In this video, let's calculate the dot product of matrix. So the mathematics is like this. We get this vector dot this vector get the first number, then this dot this gets second number, and so on and so forth. So the program is like this. We first generate n multiply n matrix, and we fill the initial value. By default, the value is 0, but on the diagonal, we fill the non-zero value. And here is a vector. We try to dot with a matrix. And it's also dimension is n. We fill the first and last slot with 1. The other place is 0. This is our final dot product. So brute force approach. We iterate through the row and the column and do the sum, and we print out the sum. So run the program, Java application. So only the first and last slot is 1. That's because matrix have diagonal, and the vector only have first and last. And according to the formula, this is our result. This approach is not very scalable because the performance is n squared, and the space is also n squared. At some point, it will run slow or out of memory. So here it's run out of memory. And we can fix this. As we observe, this kind of matrix is special because most of the places is 0. This vector have the same nature. So this kind of matrix have a mathematical name called a sparse matrix because most of the places are 0. We only have a few non-zero. So we can take advantage of this. Because of 0 didn't add to the final sum, we can ignore them. And we can use a hash map to store the index of those non-zero values. And that saves space, and also we don't have to iterate through the j, which faster also. So for example here, the hash map key should be 2 and value is 0.5. Here the key is 3 and the value is 1. And let's have a class to model that. So class, let's say sparse vector. Okay, in the center of this, we need a map. The map store index and the value. Okay, let's call it sparse vector equal new. And we choose HashMap because this is a good Java collection framework implementation of map. HashMap have guaranteed performance for insert and remove and retrieval at a constant time. Even at worst time, the performance is log n for those 3 operations. So that's good. And so now we can write a public void. Let's say add value, and we take an integer as a key and double as a value, and then we fill that as we put. Okay, and make this private because it's good encapsulation and not make our demo code longer. And if we want to check the dot, it's simple, and we just have to pass in another sparse vector, call it that. And so we iterate through the indexes, let's say key, and this is v, and we need a key set, key set, okay, and if that sv dot uh, get, okay, get key not equal 0, that means we need to increase our sum. So let's create a double sum equals 0 at the beginning, and now our sum could be this as we get key and multiply by that because it's not 0, and let's return the sum. Okay, we have this sparse vector. Now we can replace this matrix. So we can create an array of this sparse vector. Matrix equal new sparse vector with size n. And we don't need this anymore. So that's good. And we can fill the sparse vector. And let's say matrix I. And we can add a value. The key is I. The value is 1. And we can remove this. Now our sparse vector, we can create a sparse vector. Copy here, sparse vector. B equal new sparse vector. And we can fill the value, add value. The key is 0 and value is 1. And we can do it again. Add value. The key is 1. And key is 1. Key is n minus 1. The value is 1. Now we don't need this anymore. We just replace it. And the product is the same. So we don't have to iterate through the whole thing. We only have to call the matrix at position I and a dot with B. That's all we need to do. And let's run the program, run as Java application. Null pointer exception, so interesting. So here, matrix I add value. Oh, we haven't initialized yet. So matrix I equal new sparse vector. Okay, and let's run it. This time we didn't run out of memory, but eventually it will run out of memory because even the HashMap takes value, but we observe it runs faster. Okay. Stop it. Yeah, it's already gets stressed, even with new implementation, but we go much further than before. It might run out of memory or too slow. But you get an idea, like sparse, we use a hash map to store the key and the value. We just ignore a lot of zeros, save inner loop in the brute force, and we save a lot of space by not creating that n by n vector. So that's, and we added 3 0, I believe 3 0. So go much further.